Alright, so we know that in R, closed and bounded sets are compact, but in Q, that's not true. And we're going to prove that here. And so, of course, we have this set. Okay, so Q are the rationals, E is some set. We have the standard distance. So E is the set of all rationals such that P squared is between 2 and 3. So what this is this is just the open interval from negative 3 to negative root 3 to negative root 2, union open interval from root 2 to root 3, and we take this intersection with Q. So I don't know why Rudin didn't just say let's let E be the set of all P and Q such that P is between root 2 and root 3. Because having this be P squared between 2 and 3 doesn't change anything. And maybe the point is because the really important point here is the fact that the endpoints here are irrational numbers. But if what were you trying to hide that fact by writing it like this? I don't quite understand why it's not just the open interval between root 2 and root 3 intersected with the rationals. But in any case, we're going to prove that it is closed and bounded, but not compact. And then is E open? We'll answer that along the way. So, let's see here. So for E to be bounded, boundedness, we need so by the definition we need M a real number, has to be positive, and Q in the rationals such that the distance between P and Q is less than M for all P in E. So we just let Q equal 0 and M equal root 3. Straightforward. Because for all P in E, let's see here. We know that, so just looking at the set E, it is a subset of the open interval from minus root 3 to root 3. So the size of P is going to be less than root 3. So the distance between P and 0, P is the norm of P is equal to the norm of P minus 0, which is the distance between P and Q, and then root 3 is M. So there we go. That's pretty straightforward. So that's boundedness. For closeness, let P be a rational number, be a limit point of E. So what this means is that every neighborhood of P, every open neighborhood, contains some point Q not equal to P such that Q is in E. Okay. So what we want to prove is that P is in E. So let's see here. It looks like we're going to do a contradiction proof. So assume for contradiction that P is not in E. Let's see here. So P is not in E, but we know that P has to be a point in Q, because Q is the P is, we don't choose P from R, we choose P from Q because Q is the metric space that we're looking at. So since P is not in Q, it can't be in, so we have this open interval from negative root 3 to negative root 2, and then root 2 to root 3. It can't be any rational Wait a minute. Okay. So P is not in E. So no. What am I doing? P is in Q. P has to be in Q. So it can't possibly, for assuming that P is not in E, it can't be an irrational number, which is in either of these two intervals that are part of the definition of E, because the only way it could be in either of those two intervals is if it were an irrational, but it's not an irrational. It's a rational. So it has to be a rational number, and it has to be outside of these two intervals, negative root 3 to root 2, and then root 2 to root 3. So P must be in this set, and we're going to call it F. It's going to be negative infinity up to negative root 3, and then so P is in Q, so normally we would have a closed bracket here, but because negative 3 is irrational, P cannot possibly be negative root 3. Okay, so then let's see what else we have. We have minus root 2 up to root 2, union root 3 up to infinity. Okay, so F is a union of 3 disjoint open intervals, and P belongs to one of them. So there is indeed, or there is an open neighborhood I of P such that P is in, so P is going to be in I, then I is completely contained in F, which is completely contained in the complement of E. Right? Because, like, for example, if P is in the open interval from negative infinity to negative root 3, then that set, the open interval from negative infinity to negative root 3, is an open interval. And so you can just let this open neighborhood I be precisely negative infinity up to negative root 3. But it's contained in a neighborhood which does not intersect E, or is not, does not intersect E. So this contradicts that P is a limit point of E. Wait a minute. P be a limit point of E. Okay, no. Okay, so thus, so we assume for contradiction that P is not in E. We got a contradiction, so thus P is in fact in E. And so So E contains its limit points, all of its limit points, because this holds for any arbitrary limit point P. So E contains its limit points and thus is closed. Alright, so E is closed and bounded. Typically in R this implies compactness, but we're going to prove that's not compact. Okay. So now we move on to that part. To prove that E is not compact, we're going to partition the open interval from root 2 to root 3. So we're going to say x0 is equal to the square root of 2. And this is going to be strictly less than x1, which is strictly less than x2, which is strictly less than, etc., etc. Where xn is an irrational number and xn is strictly less than root 3 for every single natural number n. And we also have to assume that the limit as n goes to infinity of xn is precisely equal to the square root of e, square root of 3. And such a sequence indeed exists, because you could take x0 to be square root of 2, and then x1 to be, well, we know that between any two real numbers there is an irrational number, so you take x1 to be any irrational number between, well, maybe that's not enough. Okay, so what you need to do is so for x1, you need to choose a real number which is less than root 3, but which is also greater than the distance between root 2 and root 3. So basically, to choose, like one way that you could define a specific sequence here is that you could choose x1 to be an irrational number between root 2 and root 3, which is closer to root 3 than it is to root 2. Then you choose x2 to be an irrational between x1 and root 3, which is closer to root 3 than it is to x1. And so you can prove that, like, the distance from each xi to root 3 is going to be less than, what, like 2 to the minus n. What index was I using, I or n? Let's say I was using I. The distance between xi and root 3 needs to be less than, I think, like 1/2 times, or less than like 2 to the minus I times the distance between root 3 and root 2, or something like that. But anyways, you can certainly choose such a partition that such that the points do go to root 3. But you need to make this assumption, because if the xi's don't move to the right quickly enough, then they could converge to some other point which is to the left of root 3. Anyways, so let U, fancy U, is going to be our collection of open sets, which is going to be our open cover. So this is another reason I don't like the way that this problem is stated. So we have to make this a U union with the collection of open sets Ui, where U is negative root 3, negative root 2, intersected with the rationals, and Ui is the open interval from xi minus 1 to xi intersected with the rationals. And this is for all I natural numbers. So that's why I defined x0 to be equal to square root of 2, because that way the first open interval here will go from root 2 up to x1. Okay, so, but yeah, this is another reason why I didn't like the way that this problem was stated, is because we have to cover negative root 3 to negative root 2 separately, and that doesn't change the proof at all, but it's just like another thing that you have to do, which you could completely avoid, and you could have like a nice, nicely looking enumerated open cover if we were just looking at the open interval from root 2 to root 3 intersected with the rationals. But in any case, so we have all these sets here, and a claim, fancy U is an open cover of our set E. Certainly each set in U, fancy U, is open because each set is just it's just an open interval intersected with the rationals, and that's what open intervals look like in this metric space. So certainly each set is open. Now also note that all sets in U are finite, because the capital U is the only interval that consists of the negative numbers, and then you've got each of the UIs are clearly going to be disjoint because they sort of touch at each of the XIs, but they don't overlap at all. No, finite, what am I talking about? Are disjoint. All these sets are disjoint. Because like if you look at U1 and U2, then the right endpoint of U1 is the left endpoint of U2, and so there's no intersection there. And certainly if you consider U1 and UN for n larger than 2, then it's going to be even further away. So all sets in U are disjoint. So if U is an open cover, then there cannot be a finite subcover. In fact, if you remove, because these sets are disjoint, if you remove any one of these sets, every point that was in that element of fancy U is not going to be covered by anything else in fancy U, and thus you will no longer have a cover. So therefore, this part is proving that there is no finite subcover. That part's actually easy. Wait, haven't we done this already? Because okay, certainly they're open. Each set is open. Certainly the sets in U are open. All sets in U are disjoint too. Okay, I guess we still need to prove that's an open cover. Alright, so all sets in U are disjoint. So if U is an open cover, then there cannot be a finite subcover. So let X be in E. If X is negative, then X is in U. Otherwise, since X is in E, X is irrational, x is not equal to xi for any I. And thus, there exists some I such that x is going to be between xi and xi minus 1. No, x is going to be between xi and xi plus 1. Because if x is positive, then x is strictly between root 2 and root 3. And it's a rational number in here. And so if you look at these discrete points, eventually, if you take the limit as I goes to infinity, then xi will go to root 3. So there has to be some I such that xi is greater than x. And then you just choose the smallest one of those. You choose the smallest I such that xi is greater than x. And it can't, such a thing has to exist, and it can't be 0 because x is greater than root 2. And then once you find this I, then you choose, let's write it like this. With the way that I'm explaining it to be in this scenario. Come on, please erase. Come on. Please. Please, there we go. Okay. So you find the smallest I such that x is less than xi, and then we will have xi minus 1 is less than x is less than xi. And so what this means is that x is in ui. So fancy u covers E. Thus, E is not compact because there is an open cover with no finite subcover. But look, we've come up with a disjoint open cover of we've come up with a disjoint open cover of E, i.e. the union of all sets in fancy U contains E, but also we know that U is contained in, so for all V in fancy U, I won't use U because we're reserving U to refer to one of the sets in fancy U. So for all V in U, V is a subset of E, just by definition, or by the way they are defined. Certainly U is a subset of E, and each of these UIs is a subset of E as well, because it consists of rational numbers, which are between the necessary intervals. So because this is the case, the union of all U in fancy U, so I guess this should be V in fancy U, but whatever. This must also be a subset of E. So E is equal to the union of all sets in fancy U. But this is a union of open sets, and that means that U is open. No, that means that E is open. So that's sort of nice in that so it's always sort of annoying. Well, I guess annoying isn't necessarily the right word, but it's more difficult to solve problems when they say, is this true or false? Like, is E, the question was, is E open? They didn't tell us to prove that E was open. They just asked us if it was open. But here it's not too difficult. because in proving that E is not compact, we discovered a way of writing E as a union of open sets. And that allows us to prove that E is open. And so so a lot of these the point here is that a lot of these really nice facts about like all these nice topological facts about compactness and closed and bounded being equivalent to compactness in Rn, these don't hold in the rationals. That's because the rationals have a bunch of holes in them. There's a bunch of gaps where the reals should be. And in fact, you can sort of like redo this problem if you were to replace the rationals with the irrationals. But the interval, like instead of say all rational points between root 2 and root 3, you would say all the irrationals between you would say all irrationals between like 0 and 1, just between any two rational numbers. And you can sort of go through the whole argument again. But yeah, so the point is you need, sometimes you might think like, why do we need the real numbers when we have the rationals? In fact, like if you're working with computers only work in rational numbers. But theoretically, we need the real numbers and specifically the irrational numbers to fill in the gaps. And so this being able to fill in gaps in topological spaces is very important in topology in general. But other than that, we've done everything that the exercise asked for, and so now we're done.